Good morning. Good morning. Let me pull you guys up on my phone. All right. So today, as the title suggests, we are parameterizing custom ligands. Wait, did I save that? That's the title, right? No, I don't have to restart it, do I? Is the title right? Shoot. All right, let me hop out, hop back in. I know. Okay, does this look better? Yeah, that looks better. All right. So the title, yeah. So parameterizing custom ligands, MD for machine learning. All right. So I have to do a little bit of just like basic chores. So um, what I'm going to do right now is basically set up a simulation that I've been wanting to run for a bit with Amber tools. That's what we're going to do with. So take that off, get rid of that. Don't need that. Don't need that. Maybe we can open a new one. File. What? Let's just open the same thing. File, new window. Okay, open folder. I'm gonna go to desktop, research. So I think it's here. Okay. I haven't done this in a while. Basically, we're just setting up a simulation for Amber tools. So we first need our structure. There's a specific structure that I want to try out. I could do like a partially modified one. See what this looks like. Yeah, so I definitely want the peptide strung across here. Should I do phosphorylated? I mean, I could run two different runs, I guess. So I want to see basically if this peptide here will drag this residue over to the dehydratase domain. That's kind of what I'm after. So I need to change the names of these residues. So this needs to be HIS, CYS, CYS. So actually I don't have to change their names at all. But this has to be CYM and that has to be CYM. So I already have this downloaded. I might. I need to clean up this folder. Should I just do that now? throw everything in the trash. I think I do that. There we go. Oh, except that, actually. So we can keep this here. But everything else can probably get thrown away. All right. Download. All right, so we can open this up in PyMol. I'll play some music for me. There we go. So now I can look at the structures here and select the one that kind of stands out to us. Actions, align to this. All right. So we don't want the ones that kind of cross over here because that seems a little bit unphysical. Like that one seems decent. Not that one. This one's fine. It's pretty much the same as the first one. I actually kind of like the first one more. That one's no good. And that one's super weird, but wrong. Definitely wrong. So yeah, we'll go with the first one. Now there's other structures I could get where like this is kind of like spiraled. It makes like a helix, but we kind of want to see if that does it on its own in some sense. So this is the phosphorylated intermediate. So we want to simulate that. We could do with and without. So with ATP, I don't think that'll take very long to do. All right, so let's make a new directory. What do we want to call this? I'll start putting dates on these things. Zinc, hand off. 10, 20, 25. What? I can't do slashes. There we go. Okay, so within here, we'll do TPO 42. And then unmodified. Right. Okay, so then we need our starter files, which are right here. So we just basically copy all of that. Did it work? Boom. We'll go here, there, So now we have our starter files, and then we can put in our structure now. So do I have an automated way of doing this? Res renamer? Yeah, I think I do. All right, so what does it start with? Start.pdb. Conda activate. Amber. Drink some coffee. Some day old coffee. Let me just see what this script does first before I mess with it. What does this script do? So it runs ProPKA. Do I even have that? Yes. Sends a residue name from ProPKA. Okay. What is the input file though? Start h plus propka.pdb. Oh, okay. Start h plus. So do I need to go to the h plus server? I probably do. Which I can do that real fast. Yay. Process of structure. So what this does is basically predict the protonation state of all of the residues, and I think it moves them actually a little bit too. But you have to get rid of some of the like strange things because it can't recognize those. So like that, basically you need to remove atoms there. Then we could save this export molecule. I mean, do I really need to do all this? Hold on. So if I go to like like this. Is this an AlphaFold prediction? Yeah. Yeah, it is. Okay. So that means here our waters, and we should have all of the custom residues installed. And I assume we did we did all that stuff too. I don't know, maybe it's good just to go through it again. What is that? haven't done this in a while. I think that installs like a custom residue there. All right, let's just go through the motions. So I'm going to save this. PDB, desktop, search, L2, boom. We're on zinc handoff. We can do, doesn't really matter. Or we just leave it there, honestly. What do we call it? Start AF. Yeah. Start as fuck. Save. So you can take a look at it. Looks normal. Okay. So we can go back here, open this, and then we can give this to, I guess we didn't have to open it. H++. So what this does is basically, I already kind of said this, but it redoes the protonation state for the residues depending on its environment, and I think it'll also reorient the side chains. I think these can be left fine. So okay. Temperature is 300. Where's the pH at? Is it specified here? Am I blind? Okay. Two-stage autoprotonation renamer. What is this? Forcibly overrides. Okay. No parameters to choose. No histidine logic. Forcibly. Yeah. Okay. Well, I think that works as expected. Let me ask it. What is pH of? Why isn't it just like right here? could have swore we set like a. There's got to be like a pH, right? I guess not. Oh, right here. So why don't we have it for here? Let me look at the AMD tutorial. They don't specify pH there either. No pH there. Whatever, dude. I guess it's fine. We won't bother. But we could do 7.5. Correct orientation and assign. Yes. Fair, no. Water model. Tip 3P. 10's fine. Counter ions. Nah. Process. Oh, there's an error. Give it to me. So we go the extra mile. We do the H++ server, and then we do ProPK. So we're good boys. Add this back. Come on, man. So one thing I want to do later is, I guess I could kind of go ahead and start doing that, maybe. So I want to use ATB to parameterize the rings. But the trick is they're custom residues, so I don't know how it's going to handle like capping groups. Like I wonder if, because I use psi RESP to calculate the charges. Do they take into account cap? It would be like a charge constraint. You need to cap atoms to sum to 0. So yeah, I guess we're gonna have to do something like that. Well, this is taking forever. Let's look at the custom residues. Yeah, so it has that. Okay. So I guess we fix the charges then. And then we can do that. So if we fix the charges on the on these, then I guess we can just remove them. Hmm. So we can fix charges here, right? Charge constraints. Some charge constraints. Um, hmm. Pre-computed ESPs, okay. Feed. Okay. Okay. Adding a grid, and the grids and ESP values are properties orientation. This could be added manually. However, if we are specifying multiple orientations, generating charge constraints. Hmm. Okay, so they're doing ace atoms right there. Constraint methyl atoms plus ace atoms. Nice. Okay. Charging the restraint slope? Restrain height? What? Interesting. Okay, so we're gonna have to do something like this, I think. I'm pretty sure this could work just fine. All right, is there H++ done? Yes. Don't care, don't care. Uh, yeah, so we want that. Okay. So now we should have all our atoms in the correct orientation. For example, if we look at his, we have all those atoms there. Show sticks. Do they look different from each other? No. I mean, what? They just have hydrogens on, basically. Yeah. All right. So we can add this to, like, there's Ligand here. Then according to our residue renamer, we're going to name it this. And we're going to, I think it's this. Should work. All right. Let's do a direct path. Right. No such file or directory. Oh wait, did it do it? Wait. Start hplus.pk. Do I need to download the pk file? Is there a pk file? Okay, now I'm confused. Res renamer. Okay, so I'll put it right here. Okay, so we need to move this then. Put it like, let me just do it like this. Okay, this should work. Nice. So we should have an output.pdb with all the residue names. Right. Looks good. Just delete all. Let's look at all the residues that were renamed. So we're going to do select GO4. Is that a thing? Select res name, GO4. There we go. Plus HIP. Yeah. And then there's, what's the other one? AS4. So it looks like a decent spread. And then there's some like lysines and stuff that we're defining as titratable. How many is that already? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 18, 19, 20, 21, 22. Yeah. And there's some on the peptide as well that will be titratable. Which I think, yeah, we actually defined that as well. So we can add, so what we can do is with output, we can actually add the prediction into here. And then here, just delete everything. So we'll do action, remove atoms. So there, we can save this. Pick the wrong folder. Save it here. TPO. Save it as output. We'll just override it. So now we should have the peptide there. Yes. We might have to just do it by hand, but yeah, I think we just do it by hand, honestly. No, we don't have to do that necessarily. Could just do this. Where's the peptide begin? ADP, yeah. So we could do, is this an alpha fold? I'm not sure. Kind of looks like it is. Oh, it might not be. Yeah, it could be. Regardless, I think the names on here are correct, yeah. Yeah, we have AS4 in there. Okay, so we can go down to here. Come on. Yeah. And I think we could just copy the names. No, we gotta, there's hydrogens that are added, actually. Yeah, that won't work. We have to do it by hand. It's fine. All right. So where am I at? Um, our stuff's renamed. It's protonated. So now we have to go here. We could just use the ADP files we have been using just to keep it consistent. So now we do have a TPO residue. So let's change this to output. And then we should have this. Hopefully that'll be the right numbers, but so here we uncomment that, comment that out. T-leap minus f T-leap. So 22 atoms to neutralize. Okay. ADP does not have a type. HIE does not have the type. $29.94. That's weird. HIE should have a type. Well, no, they got HIE. I don't get it. I'm so confused right now. What is it talking about? So this doesn't have a type? It's not even named HIE. That is strange. Like, what if I rename this to HIE? Does 29 go away? It's still there. Let's see. What did I do last time? His name HIE. Yeah. Okay. Seems like it's picking up that it's HIE. Okay, so if I deleted that, I'll do that for all of them. Okay. And then I think ADP needs to be lowercase. ADP does not have a type. Oh, I see, I see. So that was right though. We need to get rid of these here. That should fix it. What? Or maybe, do I change it to this? Nice. Okay. So let's take a look, see what this looks like. Looks good. ADP looks normal. Got our TPO residue. And we have our GL4s. Now, does HIE transfer over? Is the question. Yeah, HIE does. Nice. Okay. Now, we need to change this some more. All of these need to be CYM. Yeah. So this is CYM. CYM. That's TPO. This needs to be HIP. This needs to be AS4. GL4. 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 AS4. Arginine stays the same. GL4. AS4. And that's it. Okay. CYM does not have it. Okay, so I just gotta delete the OXT atom. All right. So now we look here. The output file. We can hide waters. Just kind of take a gander. So we need to change that to ZMB. This needs to be HIS. CYS. So hopefully the zinc will come here to CYM. That's kind of what I'm looking for. That's HIP. So yeah, 894 needs to be HIS. Which it is. But I think it has something to do with like the hydrogens, like the epsilon hydrogen, maybe. So if I just delete these, that work. Well, I guess if it's HIE, it's fine, really. Yeah, because, well, actually, no, it's not. Because I think for the zinc, it needs to be named HIE for it to coordinate. But I'm sure it won't if the two cysteines are there, but just to make sure, you know. Yeah, it's still HIE again. It's probably fine. We'll see. All right, what else do we need to change? The zinc. We need to change the zinc. So this needs to be named, forgot. What does this use? Output a PDB. Yeah, so name this ZNB, right? Pretty sure. So let's do that. Pretty sure that'll work. Yeah. Okay. All right. So might coordinate to that a little bit, but it's definitely going to kick off from these cysteines and then come here, hopefully. What else do we need to change? So we added titratable residues on the peptide. We got ADP up in there. So now I think we can calculate the charges. Okay. So how many to neutralize? 27. So we put that there. We can do this, but we need to do some math first. Solvent box. What's that? Mathematica calculator. Plain text, copy that. That number stays the same. Copy this. 217. So around a 218. And so that'll be for our chlorine. And this will be 218 plus 27. And that refuse 245. Okay. That should be neutral. Yep, looks neutral to me. Okay, so if this works, I'll be shocked. Because I think some residues are named HIE when they should be HIP. Yeah, that's what I thought. So we're gonna have to go through and fix that. Where is it? Oh, BHIS. 94. So this needs to be HIP. 95 is already HIP. So now I gotta redo all that junk. So what 99 is, so we can just go through this. 99 is HIP, 102. 102 is good, 110. Good. 199. I'm just gonna see what it tells me. Glutamine 507 is not titratable. GL4. At the very end, okay, so yeah, we changed the charge now. So we'll fix that in a second. We just want to make sure the names are correct. 510. So it looks like the residue renamer didn't really do an excellent job. But the nice thing is we really have to do this like once. Are these different numbers than the res renamer? Yeah. Well, that's the problem. Hold on. Let's try and do this again. So what is this going to get rid of? It's going to get rid of the output. So let me rename this real fast to 1. Okay. So now 512 should be good, right? Yeah. 514 should be HIP. Oh wait. Where are we? 514, 512, nice. Okay. 510, yeah. Okay. So we need to basically add everything past here. Yeah. Pretty sure. Okay. And now we need to recalculate the charges again. Hello. T-leap. $25 to neutralize. Okay, so we've had this error before, but none of these are in the titratable residues, right? No, they're not. I do want to look at the output structure real fast, though, just to kind of see where all the residues are. Yeah, it looks right. There's got to be a bunch in there, because that's where the peptide's mainly interacting. And then there should be some over here, too. So, all right. So we need to modify the output. HIE or HIS. That should be HD1 H. There we go. That one should be fine actually. 102. That one's fine. That one's not fine. Okay, I think that fixed it. I'm doing well. How are you doing? Okay, so we need to neutralize. What do we need it? 25? Is that what it said? Yeah. 25. Okay, so the size of the thingy square. I need some food. Where's the size of the box? There we go. I probably scrolled by it like 50 times. Boom. Copy that. This is taking way longer than I expected, honestly. One, three. 235. 238. 213. Okay. So we can get rid of that. That should work. Hopefully it's neutral. Okay, 5 warnings, that's okay. And then hopefully this command will work off the rip. That's fine. I pretty much went all the way through. So we have to look to here. I wonder what was 1099 before though. Oh, maybe that's because we added another zinc. In previous experiments, there'd be 2 zincs. But everything else is fine, right? Like 1050. Yeah, lysine, 1029. Or no, it'd be the second peptide. Yeah, I don't know. Regardless, we can just delete that. Not in residue renamer, but in here. Boom. Okay. Now this should work. Nice. Now we have 49 residues. That's nice. Right at the limit. Okay, and then we should be able to just send this off to the supercomputer at this point. Let me double check the structure though. Got our TPO here. There's our zinc. We have CYS. So it should come off of there because cysteine needs to be deprotonated to complex with zinc. This is starting from an alpha fold structure. So likely there will have to be some temporary motions. Or like, what am I trying to say? Like initial relaxing, I guess. Because as we do know, the compactness of the enzyme is different when it's bound to a peptide. Basically, what we want to see though is if this peptide carries over the zinc to the right-hand side. I have a hunch that it will, but it might take a very long time simulation-wise. So, what we can do from here, I think we can just carry over the output file to the unmodified version without TPO installed. Paste that. Change this to output. And then we need to modify the TPO residue to THR. Just delete these like phosphate things. And so what we need to do here is add ions, comment that out. So we need 23 now to neutralize because we got rid of some of the phosphate groups. And this is our box size. You would kind of expect it to be like identical, but I guess not. I wonder what changes that. To 11. What did we say, 23, right? I let the calculator do these things because I do not trust myself. 234. Okay. So now we can change this. Let me make sure this is right. We updated our salts, right? Yeah. All right. Oh, I didn't save it. And then, is a tip 3 box? Do I usually do 30? I really don't feel like changing it now, but I'm trying to see what's like the most recent thing that I've done. Maybe here. And 30 there. I'm just gonna do 30 at the end. Yeah. What else? All right, where's this? And then we just get rid of 1099. It should go. Nice. Look at the C pin. And so the only difference between this and the first one that we did is that we no longer have, oh, we need to add ATP now, which actually that won't be tough at all, but we do need to recompute this stuff. Yeah, so this is no longer TPA. And I guess we could do one with a dehydrated residue with ATP. Oh, well, I'm glad I realized that before I started wasting compute. Set this ADP, so this needs to be ATP. I think they have the same names. ATP does not have a type. Okay. I think what we can do actually is just literally copy the coordinates from a different prediction because honestly it puts it like literally in the same spot every time. So um, we can't do A and P, right? Is A and P in there? Yeah. Yeah, I can do that. Uh, where's my prediction at? This is ATP. Zoom in. Yeah, I think if we copy the coordinates, it'll be fine from there. Why won't? Yeah, should be okay. Um, but we kind of want to copy it from here, I think. Oh, does it need to be caps? Is that it? That might be the whole thing. Oh, okay. Never mind. Let me just double check. Yeah, I mean, it looks a little wacky, but I think it'll work itself out. It should work itself out, hopefully. Um, so we need to recompute the charges now. So we need to do this again. Boom. 24. Makes all the difference. There we go. Wait, no, we need that. Boom. Boom. There. $212. 213 if we round. 227. 237. See? Can't do it. There. All right. So this would be neutral. We can do that. Awesome. Okay, so now the difference is we have one simulation with TPO, ADP, then we have another one with threonine instead of TPO and ATP. So maybe one will be like getting phosphorylated, the other one will be in the intermediate stage. And then we can do one with whatchamacallit, dehydrated. And so we could add like a phosphate there, but I don't think it's really that big a deal, honestly. So what I'll do, I forgot the name of it. I think it's ZDB. Yeah. Yeah. Okay. So we can go here, open. We can just drag and drop all of these into here. So this is with the TPO installed. We probably should do it with the threonine. So let me get rid of that. Let's see. Oops. Okay. So I know here. Okay. N1C1 C4O. Nice. Okay, so that's how to do it there. So we could put this to the side. And so so we can put this one in there. But the only thing is we need ADP. Just change the name back. So yeah. This be unmodified. Boom. So we go to output. So we want to find THR like 42. What's it called? Oh, there's a B there. Yeah. So this needs to be N1, C1, C4. We can delete this, right? This would be O1. This would be C3. Then we could delete that. And then change this to ZDB. Hopefully that's right. And we can modify this. So we need to compute the charges one last time. We also need to change ATP to ADP. I think here they're lowercase. for some reason. Python tleap. Oh, wait, what am I doing? Tleap minus of tleap. Hopefully this will work. Yay. So now we have our dehydrated residue in there. See if it looks effed. Hide the waters. Is that right? Nah. Doesn't really look right to me. Maybe it'll work itself out. Let's try to find another example of putting in the dehydrated residue. So we don't want that one. So let's look here. CDB here. Okay, there we go. Oh, never mind. So this is what the ring, replacing the ring there. Come on, bruh. I know I've done it. And honestly, what we have will probably be fine, but it looks kind of whack. Sink finger. Yeah. Right now we don't have any examples of replacing threonine with CDB. Usually I'd put like hashtags there. But it doesn't seem that that's the case. Oh, yeah, there we go. Okay. So it looks like that. So I need to revert this all back. Huh. What's kind of tricky about this is I'm starting from residues that are already prepared with amber. Uh, I mean, CG2 I know is commented out. So is OG1. So okay, I think I can make do actually. N1 is CA commented out? No. So that's probably C1. CB commented out? No. So that's probably C4. CG2 is commented out. Oh, G1's commented out. So then we have another C. So it's probably C3. And this is probably O1. That's my guess. Okay. So let's see how this looks. Nothing should change with like the size and stuff like that. Yeah, it's literally pretty much identical. All right, now let's see if this looks weird. Yay, okay, much better. Yeah, that actually looks normal. I'm kind of worried about this ATP, which I need to change that to ADP anyway. So let me change the, are we doing that? Yeah, we're doing that anyway. Oh. Right, let's check it one more again. There we go. ADP and ZDB. There's no phosphate ion, but I think we'll be okay. Can I load it very easily? I don't see it. That'll be fine. Right, so now we do some math. To 10. To 11. And we need how many to neutralize? 23. 234. To 11. Get rid of that. Comment that out. There we go. This should work. Okay. So that should be everything for 3 need 42. So let's see where that ends up. So we can drop this into, I think Narvel changed, well, I can just do Narvel. Cedar I don't even think exists anymore. Okay. Let's see, where are we at? Here. So zinc handoff. So I'm going to drop it, oops, to me. There we go. Narvel has amber, right? Yeah. What was that? That was weird. Why is my webpage so slow? Oh, it's probably because I'm sending this stuff off to the supercomputer while also streaming. Yeah, it's fast now. Okay. Oh yeah, I forgot I couldn't do that. Scratch Dominic. Zinc handoff. Okay. So now what we can do is start a tmux server. Right. Yeah. Siege-mod +6 job. Or is it? Yeah. Job automation.sh. Nice. Okay. Okay, so now that's going. Got our 3 simulations going. So we can see how those go. If they're stable, and we see interesting things, then we can go further into this rabbit hole. But for now, I need to move on to parameterizing the rings, right? So let's first start submitting jobs to the ATB server. While keeping an eye on our job. So I can get out of there, get out of there, can go here. So B, here I think. That's what we want to do. We do kind of want to figure out how to submit custom rings to AlphaFold. But I kind of want to parameterize these things first. So ring A is fine. We have our capped residues there. That's ring B. So I'm not really happy about this geometry that it has, but ring C. Ring D. So we could just submit all of these to the PDB, or to ATB server. So let's go and do that. Really, what we're looking for is like for it to be able to geometry optimize this stuff. So the net charge is 0 for all of these. Ring B. I've done ring B before, so this isn't out of the question, I guess. Maybe I should have submitted it like that. We'll see. But ring C and D have been the ones that like have been hard. C, D. Even though they're the smallest rings, which is kind of unusual. Maybe just have really like unstable. I don't know. I don't know why they don't go through. So last time I used this took around like 2-ish hours. So we'll see. But so the idea basically is to have ATB geometry optimize these structures, and then I could use the RESP charge fitting protocol that I created. But the only thing is I don't know how to, I guess we can try and do that right now with like one of the rings. So we could just do like ring A, for instance. So this would be the ACE group, this would be the NME group. Let's see. I did it in antechamber. Look at the PDB to learn what names the head and tail atoms are for residue gen. So let's see. I guess what we would have to do is generate something like that. Input files of .ac. I don't know what that is. What's a .ac file? So antechamber creates that. So we could probably do that from our RSP stuff. And then generate the .ac. Then antechamber, I think, could handle the stuff. Right? I mean, when we do the calculation in Gaussian, I think we just do the full thing. Where would I find that? Okay. Okay, this is very old, so we're not going to look at this. There's a PowerPoint. This looks kind of old too. So we do this. Oh no. I hate this website, dude. It doesn't work. Yeah, I'm not dealing with them. So let's see what this is. Ooh, this is like a paper. So what are we looking for? Okay, so usually people follow this tutorial right here, and it's a good tutorial, but it just kind of takes forever. Okay. So ESP gen. Okay. So I think an ESP dat. RSPM file right there. Okay, so do we need to generate that? I don't think so. So RESP is Amber's thing, right? Yeah, so it seems like. Right. So I think the calculation we'll do is charge restraints on the geometry optimized structure with the charges fixed on the capping atoms. Okay, one of the jobs is completed apparently. Let's see what we got here. Semi-empirical. So can we like go further? Admin only? Like why can't we do these ones up here? So what ring is this? So let's create a new folder. ATB rings. So we'll do test.pdb. Oops. Paste that in there. What ring is that? Another one completed? This is suspicious. How long did this take? 4 minutes? I don't know, fam. I assume it's ring A because it's the first one that I submitted. Yeah, it's definitely not ring A. So is it ring B? Doesn't look like ring B either. Is it ring C? Do we have a lysine? No. Is it ring D? Yeah, looks like ring D. It's flipped that way. I don't know. We'll see what the charges look like. But so this is ring D. Okay. There's the other ring. I already kind of pre-optimized the geometry with OBabel, but that doesn't really do a great job of doing it. Why can't I open it? Oh, because I spelled it wrong again. PDB. Huh? It's my dyslexia. PDB. Why do I keep on doing that? There. I mean, it looks fine to me. I don't know. Yes, this is ring C. No, hold on. Definitely looks more like optimized. Where are we at? This way? Yeah. Okay, so this is ring C. This one's probably ring B. Okay. Let's look at B ring. Yeah, so it moved that out of the middle of the ring, which I kind of like. Um, yeah, it looks better to me. So this is ring B, TP, and then ring A, I guess would get done in like a couple minutes. It's already done. E3. So now we can do this, spell it right this time. And just to make sure, compare this against that one. Yeah. So this has the, what is this? I should know this. Tryptophan. There we go. Okay. This is flat, as it should be. We'll see. So this is ring A. Okay. So I think we do my protocol, but we do restraints on the capping residues, which are right here. So do we need a mapping for those? Let's first have a conversation with ChatGPT. I thought we already had a session open, but oh yeah, we do. All right. Read this tutorial for context and await further instruction. It's crazy how fast that took. I mean, why can't we do higher levels of theory if it took so little time? Frequently asked questions, maybe. Complete topology for a default only generates for okay, less than 40. ATB will still generate. Simply contains all residue time. In some cases, initial estimates of charges may also be given before use. Examine. In order to obtain more precise, a larger molecule can be broken into smaller fragments, and the parameters from the fragments can be used to complete a template of the larger molecule. Okay, so that's what's going on then. Okay. We'll just go for it. Can't hurt. Okay. My question to you is that I am running the RESP fitting protocol with psi for on an already geometry optimized structure. This has worked well for ligands already, but for custom residues, I am wondering if at what stage do I need to apply charge restraints on the capping residues like ACE and NME. For the RESP calculation, would I just compute the charges outright, or should I force these to have a specific partial charge prior to running RESP? Here is the script I am for context. That's another thing I need to do is mess with the simulation that I'm doing. Nice. Okay, so actually one thing crashed, which that's annoying. This one looked fine. Is it this one? Yeah. Oh. So what happened here? So I think what we can do actually is for this one wait for the other ones to get through and then add the ZDB. Do I not have the extension installed? Protein. So it probably has something to do with like the ATP as well as the dehydrated residue. Yeah, that probably has something to do with it right here. And what is this? ADP? Oh, yeah, so it's definitely just that. So I put the ligand in wrong. I mean, we'll worry about that later. But I think it's 2. Yeah. All right. So where do we need to go? Desktop, maybe downloads. It's a computational project, that's what it's called. It's fine. We can get it from Box. Let me black out my screen real fast. Yeah. It's gonna take a while to download because I have some simulations in there. Next we can try and fix the threonine residue while it's downloading. So maybe we did. Like, what if we just did these four? Usually Ember can kind of build it itself just fine. Let's see what that looks like. Yeah, that already looks better. Now, does it? The nitrogen's supposed to be connected there. Yeah, and this is supposed to be the double bond here. Hmm. What if I just did like the nitrogen atom? No. So let's look at like another example. Um, yeah, so it's supposed to look like that. Well, this is connected to there. What atom is that? C4. So C4 is supposed to take the place of, what is this? Let's see. Of Ca. Ah, so this is C4, and that's C1. See how this looks. That looks better. Does it? Double bonds here. That is whack. Why is the charge not neutral? Okay. Alright, so we're just gonna have to do this the old-fashioned way, I think. So let's look at the let's see, where are these stored? Starter files, cofactors. Actually, it should be here. I don't have a PDB for it. Dang it. So maybe we'll look here. Dehydrated residues in here. No, we don't. Wait. No, we don't. There we go. Okay. Maybe this will tell me how to do it. Should be like 1040 something. Or 10. Yeah, I don't have it in here. Maybe it's a new start, actually. Here? Yeah. So let's look in here. All right. So now what we can do is compare this is threonine, yeah. Um, um, where are we? Okay, so ZDB, this is N1, That's N. So N is supposed to be N1. Okay. And so this is CA, and CA is supposed to be C1. Okay. This is C4. So this is supposed to be so C4 is supposed to be CA. Wait. I'm confused. So CB is supposed to be C3. And C5 is supposed to be CG2. And there is no OG1. So what about C? C is supposed to be here. C is supposed to be C4. Yeah. Okay, I'm good at that. And then this is supposed to be O1. Alright, so hopefully this will fix it. Oh. Does this look better? Yes, it does. It looks perfect now. Yeah, that looks normal. Okay, it should work now. But we gotta change some things around. Let's get rid of that. Do that again. 24. Where's my calculator? What? What is this? Copy, paste that there. So now we're at 213. There's 24, right? $237. Okay. All right, so that should work now. So let's go back to the supercomputer. How do I exit tmux? I forgot to do that. Oh, it's Control B. There we go. So we could just delete this whole thing. R minus RF Z dB. Okay. And we can drag this to here. Are the other one's still going? Yep. Ugh. Mondays. All right. Already got that done. So now we can just do this chmod plus 6 show. Tmux attach session minus T2. Okay. So let's see if that does any better. The other ones are running though, fine. Where are we at? Min all? Yeah. That all looks fine to me. All right, so we'll check back there in a minute. We're here. The thing should have got done downloading. So we want this script right here for Jippity. There we go. I hope the other ones have a neutral charge. right now we have PDBs, so we gotta save mul2 files, so we can do that. Just go one by one. Mul2, desktop, research, hound2, rings there. So this would be ring, A, ATB, mul2. Okay. Do the same for the other ones. Ring C. File. Ring C. Delete all. Ring D. Ring D. Nice. Okay. Okay. Lock the cap charges during RES pit. Do not let RES confuse them, fix them later. Further than Amber Star customers, you should build. Yep. Hard constraints while fitting. After fitting, strip the caps. Yeah. Okay. So we need to figure out, I guess, what the capping residue names are. This is enemy, so we'll do this one. Let's look at the tutorial. Right here. All right, so all right, we can put this to the side. So we'll do touch cap atom name index. We'll just call it capatoms.txt. Put that over there. So for ring A, we'll do underscore atb dot mul2. Do ace. So the ace atoms are this. So it'd be here. So 06. be negative 0.5679. We got C29, 0.59. We got C30, negative 0.3662, and then these are all the same. H38, H37, Thirty-seven, 38, 39. What's that number? 0.1123. Okay. All right, so that's ACE. We got to do this for each ring. And then me. So we start with the N and 6. Negative 0.4157. And then we could do the H29, 0.2719. Then we could do C26, negative 0.1490, and these are all the same. So we got H31, 30, 30, H31, right? And 32. Zero point 0.0976. Zero point 0.0976. 15727. Just double checking the numbers. Yeah, looks right to me. All right, so let's see what ChatGPT said again. Okay, so we need to change the script to accept this as input such that we apply the charge restraints to those atoms. Which I think I could probably do that. But I want to look at the documentation again. With pre-compute, yeah. So let me just copy this over. Lost network connection. Okay, update what you said with regards to how to modify the Python script with these docs in mind. Do not code anything, but construct a plan for what functions to use. All right, I'm gonna pee fast. Great. Okay, great. So let's rewrite this code in full so that it will accept. So we could just, instead of cap atoms, do cap atoms ring A. This file here the contents of this file looks like this. So each atom index has a corresponding charge to enforce with the, we can specify what to fix the charge of the other atoms to be. As a global parameter. Rewrite this code in full, please. Always ask please. Always say please. There we go. So this accepts the mol2. We're gonna label. So the total charge now will be on those atoms that are not the capping atoms. So let's see if we can do this one shot. Let's check with our simulations, see how they're doing. Where are they? Here. Yay! Okay, so we fixed it. We can't really see any structures yet. But that's a good sign. We're getting a lot done today. Obviously pins all unless the atoms to a global value, leave none to fit them. Yeah. No, see, it always adds that. That's wrong. Let's fix the total charge of all the other atoms to be as a global parameter. In this case, the atoms apart from the capping ones should all add up to be 0, or in other words, So I'm kind of concerned. So I think it should be like this. In this case, the total so with the specified charges of those atoms, the entire charge of the molecule should be in total 0. Do not change the anti-chamber command to read charges. It does this already. Trust me. So do touch psi for resp.py. And we'll do conda activate. I think it's psi 4. What is it? Yeah, I thought it was psi 4. So I need to do that. There we go. Hopefully this doesn't take forever. Come on, do the thing. It's nice how this made it planar. I'm honestly super shocked how little time that took to geometry optimize that. To me, it seems like something's wrong, but we compute how do I add a that's not right. Where's the file path to the mol2? Did it do its stupid anti-chamber thing? Okay. So I also need to double check if this is the right way of doing this. We auto-derive? Don't be ridiculous. Okay. Dude, I swear no one watches on YouTube. I don't even know why I stream here. All right. So I'm modifying the wrong script. Let me go here. And the files we want are this one. We'll call it RIA. Set that to 0. All right, let's see what happens. Great. No items to parse from RIA. Oh, bmol 2. Yeah, so is the sum of this end up being 0? Someone do the math real fast. It might be, honestly. Let me ask Google Gemini, because that's all it's good for. Ah, nice. Okay, so they both add up to 0. Interesting. All right. So ring A, I think, is the biggest one. So this one might actually take a couple of minutes. But hopefully what we would see come out of here is the charges on these atoms are this. And then we need to start thinking about like how to take off those residues. I guess what we could do is after we get the charges, if they're right, then we can just feed it into antechamber without those atoms there. I think that should work. Let's see. Residue gen. Yeah, so I think we need to create an input script. So create a .res file. Where's that? I don't see that. Prep file. Oh, I see. So I guess we can compare against the charges there. I don't really know what that means though. The FRC mod file. So this is the output right here. Server Ace and that guy. Is it done? Word atom valence. Okay. I kind of expected that. Charges don't look crazy, which is good. This looks normal. So let's look at this. So O6 has that. C29. Wait, the atom names are different. C30. All right, let's look at this. So this is oh, regardless, like I don't see any of my charges on here. So I think we did something wrong. I think we should probably go for like a smaller residue first. Maybe like a dehydrated residue and just make sure it works in that scenario. Let's just see what it says here. I am looking at the outcoming RESP mol2. The charges look reasonable, but I do not seem to be able to find the charges I specified in the .txt file here. Here is the .txt file again. The atom names are just off too, which is kind of weird. Huh. Maybe I was supposed to do N6. No, I mean, that's right. HCHHC. Oh, you know what? It might be. Okay. So it might be this. This might just have came over from the PDB file. I think we just do the dehydrated residue first. That will take a lot less time. So let's go ahead and do that. I feel like it's got to be somewhere. So this looks like that. Okay, it's around heating for one. All right. I think I have an idea. Oops. Remove the cofactor files. There we go. So go here. Like that. We want ZDB, CDB, CDB. Really, we just want this. So it should be the dehydrated residue. Yep. It's the ACE. There's our ZDB. There's our ACE, NME. Yeah. Okay, and it's flat. Nice. So we can just take this. We should rename that though. How do I do that? How's this? I think an OBabel. Server. We can convert this to smiles. All right. I might just be able to find it, honestly, with this. Okay. Then we go maybe smiles. To PDB. And this should put it as one molecule. Yeah. So let's just look at this for a second. There shouldn't be hydrogens here. It's going to add it anyway. It's fine, we can delete this. So we'll go mouse, atom, boom, boom. Move atoms. File, export structure, export molecule, save, PDB, cdb.pdb, save, yes. So we'll delete all, boom, okay. So now we go to here, submit. There's nothing matching. I mean, there should be like a hydrogen atom there, right? Or no, that's a double bond. Ah. Someone has had to have parameterized this before. So this. So the double bond here, and there should be a proton there. No. Yeah, so that's right. But why is there a double bond there? Mm. That's right. So I guess we could just submit the molecule. Okay. Preview in 3D. Let's do that. I don't know why it says a double bond there. Let's see if I can find a way to change that. Is it bond order? All right, how's it going? There we go. Boom, boom. The bond order 2. Why are you apologizing? Please eat. Um, why can't I make this a double bond? Maybe this is enough though. Oh, it's going. I'm trying to figure out some small things, really. Right now, I'm trying to make this to a double bond, honestly. It's not really working. Um, there's this protocol that I'm trying to create, and what what chemistry are you taking? All right, let's look at this. It still puts it as a Z. I think this will be fine. Let's just try it. Air pressure. So that sounds like Chem 1. Pivnert. Yeah, why is this putting it as sp3? What do you mean large? They're regular size. So this should be like 180. I could probably rotate this in a gauche. I don't know what's the most stable orientation for this. But... All right, so let's try that. So that's no longer sp3, hybridized. The names are long? What do you mean the names? Why can't I make that a double bond? Maybe I do unbond? Ah, there we go. That's what I'm after. Okay. So now if we look at this here, still doesn't have that, but can I submit it as a mol 2? I mean, I could just draw it. It's probably the best way of doing it. So let's get the smiles from here. No, I think I gotta draw it. Yeah, I don't know. I mean, this is a pretty big molecule right here. See if I can find it. I got so much crap open. This is what I'm trying to simulate or put in my simulation. This piece of work. All right, so here. So this is dihydrobutyrene. So then there's a N. Maybe like that. Boom. Oh, double bond. Carbon and carbon, carbon. Carbon and carbon, carbon. Oh, I messed up. Delete that. Bond that. Yeah. Double bond. Oh. And methyl. Well, you will. Whenever you take your classes, you understand what's going on. Really, I'm not doing anything crazy, honestly. Oh! Okay, thank God. Can I like see what this says? You both drew what? There we go. That looks right. Except this is, I think that's a Z or the S. I need to make sure I get the stereochemistry right. I can look at that. So the carbon's supposed to be oriented that way, towards the N. Okay, that's right. Okay, so boom, boom. Nitrogen. We have the ACE group. Then we have the, so that's not the enemy group. I need to add a methyl there. Maybe something like that. There we go. I'll take chemistry again, but the class that takes its place is super dope. We get to talk about allegory in music, books, and movies. Yeah, that sounds cool. You heard good things about the professor? Biology. Ugh. Biology is just memorization. All right, I'm about like 80% sure this is right. This orientation's wrong though. But okay. Transfer to submit page. So is this the PDB now? That looks right. Okay. Preview in 3D. Man, looks good to me. Submit. So now we gotta wait for that. I guess what we could do in the meantime, really, I just want to like get a PhD, honestly. What I work on specifically, like I'm studying like a protein right now that catalyzes the formation of rings on a peptide. So, like, there's actually a recent paper that came out where, like, so the GLP-1, which is like the Ozempic molecule, this is an example of like a peptide. And my protein works on these right here. What it does, it'll like install a ring right there. Auburn. Down south. It is when you like first kind of get into it, I think. But like anything, it's a lot of on-job training, I would say. You know. Oh, I think that's another thing I forgot was the proton here. Okay, so we could take this as the geometry optimized structure, I think. And just work with that. Just to see if the protocol works. How this simulation is going. Yeah, pretty much. Really, it's just like a language barrier, I would say. But once you've been in it for so long, then it's kind of you can talk to anybody and whatever they do. Like, honestly, none of it would make sense, you know. But if you're in that space, then especially with chemistry, like chemistry is one of those that like doesn't even make sense to chemists. So, but yeah, it does become more normal the more you get into it. All right, so let's do ZDB atb.pdb. Yeah, this is just what I like. It's interesting to me. So we can save this as a mol2 file, actually. this over here. You go File, per molecule, save, mol2. ZDB, ATB, mol2. We have it. Noise. There we go. Graphic design would be sick. I wanted to get into that for a while, but I don't really know how to get started. I always wanted to do like live animations in response to like music. Some people do that. I think that'd be really cool. Nice. Yeah. Yeah, I don't know how to get rid of that. What was I gonna do? Oh. So I need to create touch cap atoms zdb.txt. Okay. And so the ACE group would be that. Yeah. Yeah, feel free. Come in and out, don't matter. I'll still be here. I'm just working, so. So this is 01. C4. C5. C7. 6, 7, 8. Okay, this is N2. Also about like wishing you understood what was going on. I watched like a lot of videos about people like doing different things in like STEM, and I don't understand what goes on half the time. But I always feel like you can kind of learn through like osmosis, like passively watching or listening to something. You kind of get something out of it, even if it's like subconscious. I like to think that's true. So cap atoms CDB. All right. So first, let's just see how long this takes. Very, very fast. Good. So what are the charges we got here? That look reasonable. So now we're looking, this is like a good kind of test case right here. So let's restart this prompt that we had going on. So I think what we need to do, okay, let's rewrite the code so we accept. The file looks like this. So each atom index is a corresponding charge to enforce. We could specify what to fix the total charge of all the other atoms to be as a global parameter. So with the specific charges of those atoms, the entire charge of the molecule should be in total 0. Do not change the anti-charge. For now, let's remove all anti-chamber functionality. We just want to get out the mol2 file with the computed charges installed. One important thing to consider is that we carry over the atom names from the original mol2 file. Here is the code to rewrite in full. So we want to change this back to the original. Alright. So hopefully this will be better. How's our simulations going? Well, the trick to working longer is to keep yourself busy. Now we're on DNES. So it's going to get done in 2 hours, it says. We could actually get out a structure So I think it's Trajan, Helm1.d, or what is it? Parm. What am I missing? Oh, this one's not a DNS yet. That's what it is. Guess we do that one. Traj test.pdb right. I forgot to auto image, but let's look at this. Okay, this looks promising. So let's go to unmodified. What's the last step? Okay. This would be tret parm 7 trajan hal m1 7 auto image traj out test.pdb run. Oh, okay. Look at that. Just taking the zinc. Let's see what this will. There'll probably be like a bunch of residues it'll stick to. There's that. There's that. Lysine potentially. Hopefully there's not anything. Yeah, it could stick to there. But maybe that'll help the cysteine associate. So where are we at? We got any phosphorylation going on? Nah. That's a good sign though. Okay. Why does it always... Let's see if the other one's doing that. Parm. Trajan. Auto image, traj out, test on PDB. Run. Yeah, that one's leaving too. Which may make sense. I mean, it would repel against these atoms, but man, that would be so cool if this works. What is that? Let's see what it does. So CDB, ATP, mol2, cap, CDB. So we'll just call it this. Do we need a grid file? Yeah, we shouldn't need a grid file. Nice work. Do we have to run 2 to stage? This shouldn't take this long. Yeah, there's something wrong here. Alright, I think I'm gonna go for lunch, so I'll be back later.